Okay, so once you have your basic aerodynamic outline, look, I don't even have a body in here. You can ignore the body for the most part in this calculation. If you have something where the body is really important, like a very long forebody, which you think is going to generate lift or change the lift, you might either be able to integrate it in the main wing. If not, you will have to treat it specially differently. You can talk to me and we can handle it personally. But generally, you can actually just flatten it into the main wing and put a root cord that's extra long that models that extra length of the fuselage. Uh, Overall, believe it or not, it'll still have pretty accurate lifting characteristics. So next step is we need to define the mass properties. Now, the aerodynamics don't change with respect to weight, so we're going to model all of the mass properties for the vehicle as 1 point mass, and it doesn't matter what the mass of it is. I'm just going to put 1 kilogram. What does matter is where you place it. Since it's just 1 point mass, if I place wherever I place it ends up being the center of gravity. And the moments that are shown in the plots are about the center of gravity. Namely, what we're interested in, the pitching moment, is about the center of gravity. So try your best guess on where it should be. I would try to guess where the centroid of the planform is. So if you were to try to balance this and it was made out of some homogeneous material, like you cut it out of a constant thickness of foam sheet or something, where would you balance it? I'm guessing somewhere about here, which, since the chord is about a meter, then I'm guessing it's maybe 500 millimeters back because it was about in the middle of there. So there's more wing area here on the main wing, but then the canard also balances it out. So I'm guessing that is the centroid. You want to weight it a little bit towards the quarter chord is where the aerodynamic center is. So we're going to go forward a little bit, and then a little bit forward of that is probably where the CG needs to be. So we'll start with a guess of 400. Okay. Oh no, we lost our analysis bar. I'll get back to you. Honestly, I don't know how to bring up the analysis bar if you happen to close it. So I restarted XFLR. If you find out, let me know. Now that we've specified the mass properties, if you click masses, that 1 point mass we put shows up conveniently. And I'm like, yeah, that looks about right. Okay, so next we need to define an analysis. Go to plane. No, not plane, sorry. Analysis. Define an analysis. Pick your best guess of what the free stream velocity is. I'm making this thing fast, so I'm guessing 40 meters per second. Please, for the sake of all that's good in the world, select ring vortex that is VLM2. In my experience, it's just a little bit more consistent, and I want us all to be consistently using the same analysis method to compare one configuration to another. So we all need to use VLM2. We're going to do inviscid analysis because the type of analysis we're doing just needs the lift capability and the induced drag, which both can be modeled in an inviscid flow just fine. We don't necessarily need those viscous effects. Use plane inertia. This allows you to just move around that point mass in order to specify where the center of gravity is, instead of defining in a new analysis each time that has a new center of gravity point. Reference dimensions, use the wing plan form. Air data. Yeah, that's fine. That's all fine. Okay, great. So inside this little toolbar at the top, I now have type 1 analysis, 40 meters per second, using vortex lattice method 2 inviscid. I'm going to sweep through this sequence of angle of attack. If it's not checked, check it. We want to do a sequence to get a trend line. It's kind of pointless without it. And definitely check store op point. Otherwise, you don't store the data, which is also pointless. I don't know why they do that. So maybe every degree is probably good enough. -3 to 14 is also a pretty good range. At least for a delta wing. I expect deltas to not stall until a much later angle of attack. I want you to pick an endpoint that's near where you think it's going to stall. If you don't know where it's going to stall, just do 10 degrees, okay? We'll get to fine-tuning that exact number later. So it's going to pop up with your plane, with the reference area, all this stuff, the mass, and it's performing an LU decomposition in order to figure out the simultaneous solution of what each panel is doing to affect every other panel based on downwash, to change the lift, to figure out what the lift is everywhere. And that's what it is. So this is at 14 degrees, which is a super high angle of attack. That's why things look kind of crazy. If you look at 0 degrees, things are much more mild. Let's look at something mild, but still generating good lift, like 2 degrees. So I have a lot of things checked over here. I have lift, induced drag, and downwash. The lift is the green. Showing for each one of these sections, for each one of these airfoils, if you were to concentrate all the lift that this airfoil in this panel generates into a single point, what would it be? And it's this green line. And they connect all those green lines to give you a overall trend line. So this is your lift distribution, in this case for the canard. Likewise, they give you an induced drag distribution in yellow off the back of the trailing edge and a downwash distribution in pink. And again, you can kind of just check and uncheck all the things. It's very pretty. Streamlines look really pretty. Although they do take a bit longer to calculate. Oh, yes, beautiful. And you can see actually the span-wise flow that the lift is causing, where these streamlines get deflected outwards towards the wingtip vortices. Okay, so we're, as pretty as all those are, we're actually most interested in the plots. So since I use symmetric airfoils for everything, then our vertical force goes straight through the origin, and our CM alpha also goes straight through the origin. If you have camber, then I expect there to be some kind of offset, and that's related to CL naught, which we talked about if you were in the lecture last Saturday. So if you don't have these plots up, you can change them. Current polar, I believe. Edit. No. Current graph. Define graph settings. So X versus Y, or for some reason it's saying Y versus X, but let's change this CLCD one. It's not particularly useful. Current graph, define graph settings. Instead, we'll get a CL versus alpha graph. So F of Z in is telling you the absolute magnitude of the force that you're generating at each angle of attack. But if you just want to see the slope of your lift curve slope of your lift curve, that is your lift curve slope, you can get a CL alpha plot. At a minimum, you really just need FZ of N and versus alpha and CM versus alpha. These are the two most important ones. So what this is telling us is CM versus alpha, this slope is negative. So the vehicle is longitudinally stable. If it's flying this way and it gets a disturbance which kicks it up, in that moment, instantaneously, it's going to see a higher angle of attack, which is going to push it to the right on this curve. And as you go to the right, you get a more negative pitching moment. And negative pitching moment is, if we use the right hand rule, negative y is out the left wing, so you Take some out the left wing. It's a pitch down, curl around that negative y. So what this is saying is, in that condition we talked about, you get disturbed positively. You'll get a pitch down moment, which will correct you and bring you back in to face the wind. So that's why it's stable. So we want a negative slope there. And we want the point where it crosses the x-axis to be at 0 alpha, which it is. So in the CM alpha plot, this is like perfect. Because it's saying that not only are we stable, but we'll naturally trim out to flying at 0 angle of attack, which is the most streamlined, so that your fuselage, which is along the body x-axis, is it's just the most streamlined directly into the wind. There's no angle relative to the wind there. But the problem is that trim condition means we'll be flying at 0 angle of attack, and we won't be generating any lift because our airfoil has no camber. So what I'm going to do is I'm going to hit Shift F3 to pull up the plane editor. And I'm going to increase the tilt angle on the main wing by just a couple degrees. Yeah, 2 degrees. So now we're trimming things out. I'm going to hit Analyze again. If your analysis window crashes and says something like could not converge, that means you probably forgot to uncheck the box for viscous analysis. If you do an inviscid analysis, I've never had it tell me could not converge. So if you're still having problems with that, contact me personally, we can figure it out. Okay, so now our FZ of N is showing that we generate about 60 newtons of lift at 0 angle attack. So that's good. That is about 6 kilograms, which is a little bit shy of the weight that we're aiming for, but it means that we can probably generate our full 10 kilograms of lift at 1 degree angle attack. It's fine. Close enough. If you're generating enough lift within plus or minus 1 degree alpha, good enough for me. Problem though is we're not going to fly at plus somewhere in that bound of plus or minus 1 degree alpha, because now our CM versus alpha graph is really skewed. We are now pitching down at all angles of attack that we analyzed. And this shouldn't be a surprise, right? Because I deflected the entire main wing up 2 degrees, and that's kind of in the back, and so the lift that it generates, that extra lift, is causing a moment about the CG in a pitch down direction. So what we need to do is correct that using the canard. We need a little extra lift anyway, so hopefully by increasing the lift in front of the CG, it'll counteract that. We can get this thing trimmed out. So I'm going to put 2 degrees on the elevator, which is the finite wing section, finite wing element of XFLR I used to define the canard. Reanalyze. And I'm just going to continue this process until the CM alpha graph is still negative, and the trim condition for that is where that plot intercepts the x-axis. I want that to be within plus or minus 1 degree. And then I want the lift at that trim condition. You know, if it crosses at 1 degree, then I'm going to look at the lift at 1 degree. It's crossing at minus 2 degrees. And minus 2 degrees, we don't get any lift. So I'm going to tune it until things work out. Now, if you want to change the slope of this line, like if yours isn't negative and it's positive, then what you need to do is you need to move the CG forward until it becomes at least slightly negative. Neutrally stable is fine for this analysis. Later on, when we're doing a more detailed analysis of an aircraft that we've actually selected, then we'll care about exactly how negative it is. But you just make it more forward CG, so that would be reducing this X value, since again XFLR is somewhat of a strange coordinate system. So I'll just show you, since mine's already really far forward, really stable, I'm actually going to move it back 600. This should reduce the slope. I'll do 500. Okay, so I moved it too far back. Now it's a negative slope. So we're going to move it forward again. I'm going to try right in the middle, 450. Analyze, and I'm just going to keep going through this process. One tip I'll give you is that the incidence angle of your forward surface should be more than the incidence angle of your back surface. So you can either leave your main wing straight and deflect, well, your main wing straight and deflect your tail down, negative incidence angle, negative tilt angle in XFLR, or make your main wing at a positive angle attack and your horizontal stabilizer just neutral. Now, since I have a canard, things are backwards. So actually, to take my own advice, what I'm going to do is I'm going to leave the main wing straight and increase the angle on the canard, which is in front. The front surface should have a higher incidence angle, or in this case, it's called tilt angle. So I'm going to iterate on this and find a solution. Okay, so I finally got it with everything that we need. So I expect the plane is going to be about 10 kilograms. We generate in that ballpark. You only got to be within like 20%, we'll say, of the lift you expect to need. So 10 kilograms times 9.81, we'll just say 10 times 10 is 100. We're generating more than enough lift just by a little bit because I rounded up, right? And that's at 0 degrees angle attack. The reason why I'm looking at 0 is because that's our trim condition. I got it to trim out to 0 degrees. And again, trim is synonymous with equilibrium. I use them the same. And equilibrium is where all your forces and moments cancel out. So in this case, our lift is getting canceled out by weight. And there's no total aerodynamic moment, which means the pitching moment's 0, which is why we're looking at the x-intercept. Okay, so this is a viable solution. Now what? Well, first, we got to look at our lift coefficient. So we generated lift coefficients up to 0.7. So we're not quite done yet, because for the simulation, we want our lift coefficients that we generate, that we sweep through in our sequence, we want it to be all the way up until stall. Now, according to the Bible for aerospace, actually Raymer is kind of the Bible for aerospace we're talking about, but this is the Old Testament, that's the New Testament, we'll say. So theory of wing sections, pretty much everyone's been using it for like 50 years. There's an interesting little diagram on here pretty early on. I'm not sure if I'll be able to find it just right now flipping through it. But basically it said that as you change the aspect ratio of your wing, you change the lift curve slope. So lower aspect ratio, shallower slope, the angle of attack in which stall occurs is much, much lighter. But the interesting thing about this diagram is that no matter when your stall occurs, stall is roughly the same for most finite wings, independent of aspect ratio. They all are about 1.1 to 1.2. So, for the purposes of this first order sizing study, we're going to say every airplane that we're looking at all stalls at CL of 1.1. So what I want you to do is increase the analysis range until your lift data on the CL alpha plot goes out to 1.1. And again, if you need to change it, you go to current graph, define graph settings on whichever one of these 4 plots you don't need the most, and get yourself a CL on the y-axis, alpha on the x-axis. Okay, so I'm going to iterate on that a bit and get back to you. Okay, so holy crap, this delta wing with close coupled canard takes forever to build up any notable CL at all. So, oh, well, one problem is I've kind of detached my winglets there when I change the tilt angle. I'll get back to that, but the point is I had to go to like 35 degrees, which is ridiculous. So if you have to go past 45, then stop at 45. Luckily I was still 10 degrees shy, but past 45 it's ridiculous. Okay, so I'm going to change this a little bit, but just to show you the process, what you do is once the data is all the way you like it, click anywhere on any of these 4 plots and just do current polar, which is associated with the analysis data that you stored, whereas graph is, relating to these individual plots. Current polar, export, and go to MATLAB, Kinematic Sim, database, and you can see there's some arrow text files here. These are associated with other aircraft configurations. So what you need to do, specify this as an arrow data file by all caps arrow, and then the name of the vehicle you're analyzing. So I'm going to do Vigan Med for medium because I'm going to do some different size variants in this study. Okay, so that concludes it for the XFLR portion. Thanks for tuning in. The getting the thing to trim part is definitely going to take the longest. It's what took me the longest. Just remember to play around with the degrees of freedom you have available to you is the position of your center of gravity. Oops. The tilt angle and relative sizes and positions of your main wing and elevator. So you can slide around the tail if you got an aircraft with a tail, move it back, move it forward. That might help you get the characteristics you need to. But in general, I mostly play with the tilt angles. Okay, so actually I want to say a couple more things. I just went back and tuned the vertical stabilizer height to where it actually matched up with the main wing to account for that tilt angle, because again, XFLR does the tilt angle relative to, or it tilts about the leading edge, so the trailing edge ends up going down by quite a bit. So I brought down the Z coordinate minus 45 millimeters to get the vertical stabilizers to match up with that, the winglets. And doing that really improved the lift characteristics. So I had CL of 1.1, 3 or 4 degrees angle of attack sooner. The lift that was generated was higher. All good things. To do all this iteration, I noticed it was kind of slow with 4,000 mesh elements, so I brought it down to 2,500. And remember, this is trying to invert a matrix, which is going to be roughly proportional, I think, to like at least n squared. It might actually be higher than n squared though. But even for n squared, like cutting it in half is a big deal. It's more like cutting it in a fourth on your runtime if you cut your mesh elements in half. So I mainly took that out of the main wing because I remembered from my example I had huge numbers. Yeah, you don't want that many panels. So just aim for a good distribution of somewhere around 2,500 panels, I think is a good amount to aim for. So that's pretty much it. Okay, now we can do MATLAB.